this computer. Very good. Okay, awesome. Do you know if any InstaDeep people are coming along?
No, I haven't specifically invited anyone. I didn't know we were supposed to.
No worries.
Sorry.
No, all good. That's perfect. Are you still collaborating with anyone from Stellenbosch?
Not particularly at the moment. So I did my master's at the end of the last year. So I think you're even one of my examiners for that. Thanks.
Sure. Pleasure.
Yeah. So since then, not really. But yeah. So how's like? So I don't actually know much about this lab.
About Shocklab.
Yeah. Yeah.
Okay. We are a medley collection, a random selection of people doing masters and PhDs and honors projects with me. I guess it started out really as the name of my website, and then became a thing after that. So it's not that I sort of set out, I had some dream of having a shock lab, although now it's very nice to have so many people within this community. So yeah, it's more like a sort of a loose community of people working together on overlapping things. And it's I think it's
cool.
Growing to be quite a strong group. Yeah.
Great.
Okay, very good. Cool. We got a few more people along. This is great. I think there might be a couple more coming. But yeah, let's get started. So we're really happy to have Kevin Eloff here today, who did his master's at Stellenbosch University and is now working at InstaDeep, which many of you know, working in BioAI. And today he's going to be telling us about denoising diffusion models. Go for it. Thanks.
Awesome. Thanks, Dr. Schock. Thank you, Sinjin, as well, for inviting me. It's really cool to be here. Nice to see you all. Yeah, so as Dr. Schock mentioned, I'm going to be talking about denoising diffusion models and just roughly going into some of the introduction applications of that. So the main thing here is we wanted to be able to generate images from text, right? I will be covering some other things, so you don't necessarily have to do images from text with diffusion models, but I'll get to that later. It's become like the most widespread use, at least. So like you can see, these are some really high quality, very cool looking images, and they're all built by a model or made by a model. So it's quite a fascinating application of generative models. And ideally, we want to be able to generate high quality samples that are out of distribution from our training set, right? So like maybe I've seen a lion, maybe I've seen an astronaut, maybe I've seen Mars. I've not necessarily seen the combination of all three of those things, but can I be general enough to make something that is combining all three of those things together? And that's really the main thing that we want to be able to do with models, and also generate multiple images. That's also really important. So in the examples here, here it's just a person with a ring in the rain in a raincoat with a close shot, so it's like very close to the face, or a cat in shining armor, any detailed armor down there, and then on the bottom right is a astronaut riding a lion on Mars. Yeah, so you can see it does work. Another really cool thing we can do with this is we can actually sample, because these are generative models. So I can just run the model again with a different seed, and I'm going to get different outputs. Some interesting things to note here, though, like it's not 100% perfect. Like this lion actually has 5 legs. Well, this one has 2 claws, or a few other things, but there's also some really cool things you see here as well, like this astronaut's taking a selfie with his lion. There's some interesting details, like the lion actually has a spacesuit on. These are all really, really interesting results of these crazy powerful models. Yeah, so, but otherwise, I really like some of these images. They look quite nice. So I guess this talk is taking a very, very light dive into how these are actually made. Yeah, so how do we do this? And the answer is, over the last 2 years, we've made some massive advances in the field of image synthesis with generative models. And the core of all of these state-of-the-art models is actually powered by denoising diffusion. So for example, we've got Dall-E 2, that was one of the first ones. It wasn't so great, but then came along Midjourney and Stable Diffusion, and those two are crazy good. There's a few others like Imagen and yeah, a few. Yeah, so let's dive into denoising diffusion models. So maybe just quickly the scope of this talk. I'm going to be focusing on denoising diffusion models in general. So I'll just basically cover the fundamentals of DDMs. And then there's two processes that we'll cover for that. Reverse noising process, and then just quickly cover the maths and formulation requirements. I'll also cover how these models are trained, how we do inference on these models, and some various decoding techniques that we can do some fun things with. Along this talk, I'll also be just quickly taking a look at something called multinomial diffusion, which is like an atypical application of diffusion, just showing you that it can work for something that isn't images, which is really cool. I'm not really going to go into the details of the model architectures, so they use like a unit. I'll just briefly cover that. I'll also uncover super resolution and latent diffusion. Yeah, so what are denoising diffusion models? So as I mentioned earlier, they're a variant of generative models, and the process basically involves iteratively adding noise to an image and then iteratively denoising the image. So on the far left here, we have some like complete random Gaussian noise. Can we take this and iteratively go to a picture of a dog? So we know the final image is a dog. Maybe we didn't know that this was a dog in the middle here, but can we like take these little incremental steps that's going to lead us to a final high quality image? So instead of just saying produce the dog directly, we're going to say iteratively move towards producing a nice high quality picture of a dog. So to do this, we define these two processes. We have the forward diffusion and the reverse diffusion. So the forward process is then adding the noise. So here we have a dog in the bottom left, and then we have this distribution Q given xt, distribution xt given xt minus 1, and that is basically what will the next image look like given the previous image, where the previous image is a less noise version of the next image. And we're going to iteratively keep adding noise until we have something indistinguishable from the starting point. And then capital T here is just like a hyperparameter. It's usually set to like 200 for these models. It's just the amount of total steps that we're going to be adding. And we also have the reverse process. So that's where we iteratively remove noise. And that's usually given some targets. So in this case, this should actually be conditional on x0 as well. But this is the model's output, so they sometimes don't do that. This is also sometimes subscript theta to show that it's using the model parameters. But basically, it's defining the distribution over xt given xt plus 1. So how do we iteratively remove some noise? So given a noisy dog, can I get a slightly less noisy dog in each step? And that's the two processes. I'm just going to quickly say that if anyone has questions, you can just stop me and just interrupt, because there is quite a lot. Cool. Just very quickly, I'm going to go through some of the requirements for diffusion models. So basically, if you can meet these requirements, you can apply this to basically anything or any data. It can be text, it can be images, it can be audio, for example. The main thing is the forward noising process must be reversible. So the forward noising process is when we add noise. It's really easy to add noise to things, but we have to have an integer actually removing that noise again. So given some target x0, we should have a way of removing that noise. So a very naive approach would be like interpolating between xt and x0. So you can just, if you know what x0 looks like, you can just, yeah.
Can I ask a quick question here? So you wrote there, you've got your p of sort of x1 as a conditioned on x0. Should I think about this probabilistically? In which case, how is it reversible? Given that, yeah, it's non-deterministic.
Yeah, both. Of these, the forward and the reverse processes, I'll get into the details very soon, are actually Gaussian samples, so they're Gaussian distributions. And it's kind of strange, like removing noise, but you're also sampling a Gaussian distribution. How does that make any sense? But it's, you actually condition the mean for x0, so you're basically nudging it in the direction of your x0, and then your variance is also dependent on your t, but I'll get to that in a few slides.
But within this process, you say it's reversible. Will you always get back to exactly where you started if you're running over both of these?
Yes, so given the noise schedule and So this one over here actually isn't deterministic. So this one is deterministic, sorry. The rest are stochastic, but this final step would be deterministic. So x1 actually becomes x0 because it's also conditional on x0 here. Because in this case, your mean is equal to x0 and your variance is equal to 0 in the final step. But we'll see that in the equations pretty soon.
Okay, sure, yeah.
But yeah, so it is kind of strange. In each step, this is jumping the gun a bit here, but in each step, the model is predicting x0 hat, so it's predicting what the dog should look like, and then you're iteratively moving towards that picture of the dog. Yeah, so maybe it's not like the most clear wording here, but basically, if I have something that's noisy and if I have some target, can I move towards that target? So I guess the distributions, ideally, they should be pretty similar for xt given xt minus 1 and xt minus 1 given xt, but sometimes it doesn't have to be that way. Yeah, so we just want to be able to go into reaching our dog. So what direction do my pixel values have to go in to actually reach my dog? And the other requirement is that at x capital T, this one is not necessarily true. This was more of an early requirement for diffusion models, but they've proven that you can actually go in any direction. But you want it to be random noise at x capital T. So all the noising steps, you want it to be kind of indistinguishable from your original image. In that case, we have like a many-to-many relationship. So any starting picture can become any random noise, and any random noise can become any starting picture. There is maybe not the best, but I hope that makes sense. It'll be a bit clearer pretty soon. Yeah. As I mentioned, we can do this in other domains. So here's the forward and reverse processes for a text sequence, for example. So say we've got this x0 Mr. Quilter. We can iteratively corrupt the sequence, or we can iteratively reverse the process and correct the characters. Something to mention here is all of the characters and also all of the pixels are actually conditionally independent of each other, which might seem strange, but it's in these actual reverse and forward noising functions, they're actually conditionally independent. They actually don't look at each other when they do these calculations. It's only the model itself that's able to like sort of attend over everything and sort of say what needs to happen, which is, yeah. So getting into the simple one, which is adding noise. So this is the forward process now, just getting into some of the equations for images. Firstly, I'm going to be defining this or alpha t, which is our noise schedule. And it's basically a set of scalars for each value of t, and it is monotonically decreasing between 1 and 0. So for a cosine function, for example, or a cosine decay, it'll, I'll show it in a few slides, but it'll go like starting from 1 and then slowly decrease until capital T, where it'll suddenly drop towards 0. And then we can actually define this distribution. So qxt, so the distribution of xt given xt minus 1 is our Gaussian distribution. So it's over xt, and this is our mean, and this is our variance. So we just take the square root of our current or previous time step of the noise value and multiply that with xt minus 1. And for the variance, we take 1 minus the noise schedule. So at the beginning, equal to 0, this value is going to be close to 1. So your variance is basically so you're not going to be adding a lot of noise at the start. But as you increase t, your alpha t is going to start decreasing, and then you're going to be adding noise, and you're going to disregard your xt minus 1 more. Another useful property of Gaussians is if we keep applying them to each other, we can actually sample xt directly given x0. And this is just useful for training. So we don't want to, in training time, iteratively just keep repeating the function. We can just sample directly xt given x0. And that looks like something like this, where our mean is now relative to this alpha t bar. And this just comes straight out of the derivation. If you're interested, you can follow the link below. But alpha t bar is basically defined as the product of all of the alpha up until that t value. Yeah, so the forward process is relatively simple. It's just adding noise to an image, Gaussian noise in this case. The reverse process gets quite a lot more intense, but I'll slowly break it up. Most of these are actually just coefficients that come out in the equation. So, but the intuition behind it is actually relatively straightforward. So we can define the reverse noising process as the posterior or distribution over xt minus 1, given our xt and our x0. Maybe let's cover the variance first. The variance is kind of similar. So for small values of t, the variance will be very small, we're not noise. For high values of t, this is going to be tending towards 1. For the mean, though, what we're actually doing here is we're interpolating between our xt value and our x0 value. So for small values of t, we're actually going to be favoring our x0 because alpha t here is going to be close. Well, I think it's actually, we have to look at alpha t bar because it'll be weighed more. But yeah, basically this coefficient here is going to be favoring x0 than xt. So it's kind of going to start ignoring this. I'll show that on the next slide just as a little example. But that's the main thing that happens here. So we have this like sort of interpolation between x0 and xt. Yeah, and then we can also define our p function. So this is the diffusion process parameterized by the model. So here we no longer condition on x0, but we actually include x0. So where in the previous equation we have x0, we now have x0 hat. And the model basically defines the distribution of x0 hat, and that is defined as follows. So the model here can take in some conditioning, and it takes in our current xt, and it produces x0 hat. Yeah, this conditioning here, it's usually like a clip embedding, for example. That's the most common one. So OpenAI's clip model provides really rich text information or text embeddings for the text encoder portion at least. And it turns out that works really well for these image generation models because it's already like sort of latched into the image domain. So then you just freeze that model and use its outputs directly and condition the model on that. So this C here might say a small dog, for example, and it'll capture that information. And then the model might attend over that. It'll also attend or use a vision transform or a UNet or XT, and then produce a distribution over X hat, which we can then sample and put into the equation above. Yeah, so maybe just give a quick example of what's actually happening there. So I was mentioning the interpolation, and this is what it would sort of look like. So let's consider like a single pixel value or a single scalar where the values range from 0 to 1. Let's let our current value of xt be about like 0.25, for example. Maybe our x0 is 0.25, 0.5. And this is sort of what our distributions over xt minus 1 might look like. So for a large value of t, you see the Gaussian is quite wide and it's close towards xt. So this is the interpolation I was talking about. So it's kind of disregarding what the model's actually outputting, but it is slowly nudging the image towards that, or in this case, the pixel towards that value. But as t starts decreasing, you see the Gaussian actually becomes narrower and our value of x0 more. Yeah, so let's consider just an example given an image. So here we have our noisy image at xt. Given this and the conditioning, the model will predict x0 hat. And then using that equation reverse process, we can actually sample xt minus 1. So this is an input, model predicts this, and this is the output at the end of that inference step. I've also just mentioned here the loss function to train these models. So we have those two distributions, right? For the The one is conditioned on the ground truth, and the one is conditioned on what the model's outputting. So we just simply take the KL divergence between those two. And that's actually the loss function. So it's actually relatively straightforward. It sort of makes sense. So model thinks the distribution over xt minus 1 should look like versus what the actual distribution over xt minus 1 looks like. For those who don't know, KL divergence is like a sort of metric to compare distributions. Just for completion's sake, I'm just going to quickly go over the multinomial diffusion as well, just because I mentioned it earlier. I won't go into too much detail, but it's essentially the same thing. So instead of Gaussian distributions, we now have categorical distributions. So we just change the logits per vocabulary entry. In this case, we use beta just because it simplifies the maths a little bit. Beta is just 1 minus alpha. But once again, you see this sort of interpolation between xt and x0. So this actually comes from our paper from last year where we did this at SACE, and we used multinomial diffusion for automatic speech recognition. So we were like, could we reverse the process? So instead of going from text to images, can we take images, or in our case, spectrograms, and predict text? And it turns out it works pretty well.
Sorry, could I just quickly ask continuous time case, because I know that there are different formulations. How does that look compared to I think that was the discrete time case that you showed us earlier?
What do you mean by continuous time? So all of these are discrete time steps if you're talking about t.
Yeah. I'm just saying that I'm aware of diffusion models that are not, they don't work in discrete time steps. I'm just asking if, like, how does that work?
I wasn't aware that those existed, to be honest.
Okay.
Yeah, I have no experience with those. Do you mean like they're like in this t here? So this is continuous. Like there's no, or maybe like between the images. You're saying there's no discrete set or steps here.
I'm not exactly sure how it works. I've just seen it mentioned in papers. People can formulate it in terms of discrete steps or in terms of some sort of continuous thing.
Interesting. I'm not aware of that actually. I suppose technically the maths would still work. Yeah.
Presumably one could formulate so basically what you're looking at here is you're taking the distribution and you're stepwise moving the distribution in some deterministic way. So even though you may sample from it stochastically, you're shifting the distribution, and you could write down a differential equation that describes the movement of that distribution. And then so is the point about this being reversible that you shift the distribution and any draw from the distribution will be stochastic, but at the end, because you're taking the mean of the distribution, that's the value that you take, that means that the process itself is reversible.
Yeah. That actually is shown here. So this is like our target x0. Xt is like what we currently have, and you can see that because the mean of our Gaussian has been shifted so towards x0, we're actually like removing noise. Like no matter where along this Gaussian we sample, we're still moving in the direction of where we want to go.
So really one has to keep track of the entire distribution through the process, rather than just sampling particular values from it.
Yeah.
Okay.
In practice, I don't even think we sample it at all.
Okay.
I think, we kind of just run with it.
Okay.
Well, I guess we do actually sample the Gaussian distribution, but then we just scale that. Yeah, it's interesting. Good point. Yeah, sorry, I don't know if that answered your question. If you can point me towards some of that literature, I'll happily take a look and see what's going on there. Yeah, so maybe just going back to the example. So this is once again what it might look like for a trained model that's doing multinomial diffusion. So once again, we have our corrupted sequence on the far left here. And the model actually learns to output logits in such a way that it's able to iteratively denoise and eventually get to the ground truth, Mr. Quilter. So this was an actual trained sample. We gave it an audio file. if some of you have ever worked with library speech, you might know that one of the first validation samples is Mr. Quilt is an apostle of the Middle Ages. So that's what we're seeing here. I'm also showing here, just as an example, what our alpha and beta might look like for a cosine schedule, and that was used for this transcribing speech with multinomial diffusion paper as well. So you can see here where alpha is very high or very close to 1, as t is small, and then starts adding quite a lot of noise towards the end. Yeah, so maybe just to give a quick summary before we actually jump into the training and inference. So we have these two processes, the forward and reverse diffusion. In the forward process, we are adding the noise. So we have firstly the distribution over xt given xt minus 1, and then the nice little helper function, I like to call it, the distribution over xt given x0. And then we also have the two reverse diffusion functions. The first one being a distribution of xt minus 1 given xt and x0, and then the one parameterized by the model. So I mentioned this earlier as well. Sometimes people put a little theta, subscript theta for that p, just to show that it's conditional on the weights theta. And yeah, so that's the distribution over xt minus 1 given xt and whatever the model is predicting. And just I've also just reminding you what the different xt's might look like. So you see xt minus 1 is a slightly less noise version of xt. Cool. So jumping straight into training then. Training is relatively straightforward actually. So in each batch, we'll sample our conditioning, represented with C here, an x0 and a t value. So it'll be different for each batch item, but yeah, so we'll literally randomly sample the t. So maybe it's 5, 10, 100, 20, 30. And then what we'll do is we'll take our x0 and noise it accordingly. So take that little helper function I mentioned earlier and sample an xt given that, given those t values. So let's say t equals 100, it'll noise our image by 100 steps, feed that into our model, feed the conditioning into our model. So in this case, a small dog, which goes through our frozen clip model. You can pre-compute these because since this model is frozen if you want to. It will speed up training quite a bit. So we feed both of those things into our model, and then our model produces our prediction of x0 hat. And then we can just run those to get our two distributions, our p and q. And actually in practice, so this is the case for images at least, some smart person went and did the derivations, and you can actually approximate this or this by using the L2 or mean squared error loss between x0 hat and x0. So you don't even have to take the KL divergence at all. If you look at that LUOC earlier, I'll look at the end as well. They go through that full bit derivation, but yeah, so it's actually even easier to train these models than you thought. You just take the model's output, compare it to the original image, and there you go. Maybe I should also mention here, this isn't the only way to train. Some people also predict the noise, so you don't have to necessarily predict x0 hats. You can also predict the difference between x0 and x0 hat. Sometimes it also improves performance because they find that the noise is actually slightly higher frequency, but I've never really done that in my side of things. So I've always just stuck towards predicting x0. It doesn't seem to make that much of a difference in my case. Yeah. So does that make sense? I hope this is like sort of straightforward. Cool. Maybe just to cover what the model would look like. So this is a unit. This is the most popular one for, it's basically used by all of these models, or all of these like Midjourney and Stable Diffusion. I'm not going to go too much into detail here, but basically it's a bunch of ResNet blocks, and they've got spatial downsampling at the encoder side. So it's kind of like a autoencoder kind of architecture where they have some spatial downsampling, and then they do some spatial upsampling again. These blocks here are the time step embeddings. So one important thing is we actually have to tell the model what the current time step is, so it helps it make the prediction, and also the conditioning would go here. I guess the intuition here is that it can do like sort of option at this bottom layer and then do the high frequency details with these top layers. The main thing to note here is given some input image of some size, it'll output an input image of the same size. So inference. This is also actually relatively straightforward. We basically start from a completely random sample, so mean 0, variance 1. And we just iteratively denoise it. So we feed that as the first prediction into the model. The model predicts its x0 hat. We can then feed that into that reverse function to sample xt minus 1, and then repeat. So we just keep on repeating this until we get our x0. Yeah, that's super straightforward actually. Like you just feed it into the model, get a prediction, feed it back into the model. Maybe just to give a quick example of that, it might look something like this. So starting from complete random noise, the x0 hat might look something like this. And then like as it moves along, it's slowly moving towards that final x0. So this is at t equals 150. We have like something very slightly represents this a. And you can see the models are putting like a less noise version and so on and so forth. And eventually we get our a. It's kind of funny. I actually trained this to do MNIST digits. It's not supposed to be an a, but yeah. I was doing this for the prac for the deep learning in Dall-E that's coming up, and I think I had something wrong with the model, so it's an A. Also just got a quick little video here showing the iterative refining of the A. Yeah, so it works pretty well. Obviously, this is a super simple model. It's actually quite fun to look at the bigger models. Most of them are latent diffusion models. Maybe I'll just quickly mention what that is. So instead of diffusing on the like input and output image, they diffuse the latent space. So they actually train like an autoencoder and then diffuse in the latent space of that autoencoder. Yeah, there's a few things there or caveats there like that actually break the maths, and there's like lots of derivations and things that you have to need to do to actually make sure it still like works out in the end, but it seems to work pretty well. Yeah, so maybe jumping into some inference tricks. So there's some things you can actually do to improve your model. So this is like independent of training. So once you've trained your model, you can just apply these things and it'll just make your output better. So one of these things is classifier-free guidance. So what we do is during training, we occasionally drop the input conditioning. So you won't tell it what it's trying to generate. It just has to try and figure it out on its own. And that kind of lets you actually do unconditional sampling of the model, but it also lets you classify free guidance. So what you do is at each time step, you have two versions of the model conditioned and the model unconditioned. And basically the intuition here is you actually move in the direction of the conditioned model from the unconditioned model. And you can do that with the weighting. So it's usually about 1.5 or so. I guess the intuition there is if I don't know what I'm supposed to be moving the direction where I should go, there should be, you will like move in the direction of increasing conditioning by moving towards the condition model.
I think Hugging Face's Stable Diffusion actually does this slightly differently, interestingly. They only have one model. I don't think that they drop conditioning during training, and they compute the unconditioned output by giving it the empty string as a prompt.
Interesting.
Which is kind of like a trick that they have, I guess, to approximate classifier-free guidance without having to explicitly have two models.
Yeah, so sorry, I should mention that this is the same model, but it's just with and without C. Like you would do this during training anyway. It's good for your regularization. Yeah. Cool. Yeah, so another thing you can do, and this is actually from the in-painting paper. So there's like the sort of resampling. So during inference, what you can actually do is, in the inference I showed you, we don't do any like adding noise besides like getting the initial noised image. What you can do is you can like do 10 steps of denoising and then like another 5 steps of adding noise, and then 10 steps of denoising, add noise, etc. And it actually sort of like it improves the local coherency and sort of helps prevent those like the lion with 5 legs. Yeah, it actually, yeah, it makes pretty big improvements, and it made a pretty big improvement on our text diffusion as well. Another really cool thing you can do is inpainting. I really like this. I think it's really cool and really powerful. Basically, you can mask out regions of the image that you want the diffusion to be applied to, and then tell it to sort of leave the rest of it alone. So like, for example, here we have some lady with a mask on, and then we can sample multiple variations where the inpainting has only affected that region. So they're making different faces. You can see the face is like pretty inconsistent. The nose looks different, sometimes smiling, sometimes frowning, etc. But it seems to work pretty well. I'll go through how this works in the next slide, but there's some pretty cool things you can do with it. So like here's a bowl of fruits, and they just say take the middle portion, and right now suddenly it's made a bug or some strange looking spaghetti or some leaves. Or like at the bottom here, here's a shed, and they mask out the right side, and they say only diffuse there, and oh, here it's built a shelf, here it's built like the rest of the shed, some other stuff, or here it's put a person. So it's pretty powerful. You can do some pretty cool stuff with that. And the way we basically do this is we take our input image. So this region here is where we don't want to add noise. And this is where the model is going to be working. So we add noise to it. And where we add noise, we don't consider the model in these regions, but we only consider the input in the non-masked regions. So you can see how we cut it out here. So this portion of the image at xt-1 will always be relative to the original input, but the masked portions will always be denoised by the model. So even though the model makes a prediction on those locations, it sort of gets cut out and given the ground truth again. So the model still sees like a noised version of the original input at each time step, as it's like doing the iterative noising, but it only actually gets to like have a say on the region that is masked. So as far as the model's concerned, it was the one that output this region here. So it's like kind of like a fooling it. You never have to like train the model to do this. You can just do it during inference. Yeah, so it seems to work pretty well. Here's an example where they used p subscript theta. Yeah. Yeah, so just to end off with some interesting things. So I don't know if any of you have seen this, but I think this was at the end of last year. An AI generated picture won an art prize, and obviously artists weren't very happy. Well, digital art competition, so I guess understandable, and they didn't really have rules against it, but it's an interesting moral thing that we sort of need to think about, like what sort of effects do these models have? It's pretty crazy that a AI can generate such a high quality image. It looks really cool. Yeah, some fun examples of these models. You can make them make, I think I asked it to make a meme, and this was Joe Biden and Trump playing Minecraft. It does it pretty well. It's not amazing. This was with the free version of Stable Diffusion. Another really interesting thing to note here with text is it seems to sort of come up with its own language. I still haven't included this example, but I will in future presentations. But there was once someone asked it to make a speech bubble with the word apple in it, and it gave like crazy weird text. And then they took the weird text, like it was still like characters at least in English, and they fed it back into the image generation model, and it actually just started generating images of apples. So there's some weird, between Clip and these diffusion models, it's coming up with some weird language. I don't know how it's doing that or why it's doing that, but it seems to do some pretty strange stuff. Yeah, it's quite crazy. Here's a slightly better model. Literally just the prompt funny meme. It's a very strange looking cat, but yeah, it also doesn't really, I am Saythok. Interesting. Almost looks like a different So it tries to make things that look realistic or look consistent, but it doesn't really have any context of what it's trying to do, which is interesting. But I feel like in a few years it might be able to actually do that pretty convincingly. Like it's come along since like last year. Yeah, funny meme about engineers. That's some weird looking mouse or something. Yeah, this almost looks like a article of some sort that is like a screenshot that is trying to generate. Almost looks like it's got like the share and like buttons at the bottom there. Really interesting. It's cool to see that these models can do this sort of thing. Yeah. Finally, just to end off, so here's some further reading if anyone's interested. Firstly, I want to talk about that there's a diffusion practical from last year on the deep learning in Java GitHub that was done by James Ellingman. We'll also be presenting a practical at the 2023 Indaba in Ghana if anyone's attending. His practical is quite interesting though because it takes a deep dive into the probabilistic theory, which I didn't really cover. Some papers that are interesting. So this understanding diffusion models, a unified perspective, was really interesting for me. They go through the maths very heavily. So if you're interested in any of the derivations or why it works, how it works, I would really recommend that. The in-painting paper is really interesting as well. And then our own paper where we did this for multinomial diffusion. Yeah, otherwise you can just reach out to me at k.eloff@instadeep.com. Cool. Questions?
Well, thank you so much, Kevin. That was fascinating and very clear. Yeah, does anybody have any questions? So I have a couple of questions. Actually, I've got a load of questions, but I'll start with a couple of them. One thing is that it feels in some senses a bit like, or it's got parallels with simulated annealing. And one uses simulated annealing to solve certain physics problems. You've got some constrained system and you set it up with a temperature, and you let it essentially settle into some local minimum of a potential or whatever. Is there a way to use these sorts of models to solve physics problems? Do you know?
Oh yeah, for sure. I guess it really depends on the problem. Yeah, so one thing I didn't really cover in this talk is why does it work? Like, why is this so much better than just predicting the image from scratch? Like, why is this like sort of iterative process so helpful? And honestly, I'm not too sure. I don't think people really know yet. I think it is like learning this one step at a time it really helps the model like fine tune itself, and it almost never overfits. But that's kind of tangential to your question. For physics, I think definitely we're actually using it a lot for biology now. So like at InstaDeep, we're doing it for like different bio applications. I'm doing it for text diffusion as well. But like biological structure, it works there quite a lot. So I'm pretty sure it works for pretty much most physics as well. I guess it really depends on what you're doing, what your problem is. But it has some really interesting applications in like structure stuff, like predicting like what things look like, how they move. Yeah.
And then sort of following on from that, so you can think that you've got this distribution shifting, and your network is trained as to how the distribution should shift, which feels a little bit similar to the way a neural ODE is it's a limiting. It's a particular limit of taking a recurrent neural network, which is sort of applying something again and again and again. And it's taking the continuum limit. So I wonder, in terms of Tim's question, actually, about the continuous version, whether there is a way of thinking about a neural ODE as a sort of diffusion model, but the ODE is defining the shift in the distribution along each step.
I mean, it should work. It's a very good question. So the way that we're currently doing it, like the reason we have the discrete steps is you have to like choose a point where the model actually makes an output, makes a prediction, and then like you move in terms of that interpolation. You could do like sub-time steps if you really wanted to. I wonder then if you could use that neural ODE to kind of smooth that out even further.
Well,
that's a really good point.
In a sense, it wouldn't be about smoothing it out. It would be about the fact that you could basically, you could take it from the beginning time step to whatever time you want into the future. And so you could extend it rather than just, you know, looking at smaller time steps.
Interesting. That's a good point.
In a sort of semi-deterministic way.
Yeah. I wonder if that would also like help speed it up in some sense.
Yeah,
so
exactly. So you wouldn't need to keep iterating. Yeah.
Yeah. So one thing that they often do is like they'll train it for 200 time steps, and then they'll do like an interpolation where they only make the model predict every 5 time steps, for example.
Right.
It'll decrease your overall performance. Like your images might not look as good, but it'll significantly increase your inference speed. Yeah, I don't think that's exactly related to what you're talking about, but it is.
Well, I think it is, because I think essentially if you can encode the whole thing as a neural ODE, then you could just do a single pass. You wouldn't even need to do multiple passes.
That's really interesting. That would be really powerful if you could get that working. Yeah.
No, if you could get it working, I definitely can't.
I don't actually work in diffusion models that much.
What's that?
Sorry, can you hear me?
Yeah.
I was wondering if that would be like trying to encode like a master equation for the shifting. Is that what you're trying to do?
Yeah, exactly. That's exactly right.
Okay. So you're trying to learn the master equation that is leading to this sort of performance. I see. Okay.
Yeah.
So I guess that would be more like the distribution of x0 given xt, but like overall time steps.
Exactly.
Yeah. That's really interesting.
Oliver, you had your hand up and then took it down. Did you have a question or?
I think Tim's question might be to do with the current question before I go off on a tangent. So you can go first.
Yeah. Tim?
Yeah, I'm gonna link a paper that talks a bit about the continuous time stuff. I don't really understand it. And they also talk about interpreting one of the like popular samplers as a neural ODE. And I'm aware that OpenAI released this paper, I think they're called consistency models, where they try to do diffusion in a single step by modeling the whole iterative process as like a stochastic differential equation. They try like solve that. But I've also seen an alternate technique called progressive distillation, where you train one model to do what another model did in 2 steps, in a single step. And you keep repeating that process until, in theory, you can approximate 1,000 steps in 10 steps. I was just wondering if you'd played around with anything like that in practice, like if you managed to get good results. I've only seen, papers on this. I haven't actually seen a practical implementation.
Yeah, I've also seen quite a lot of this, where people like sort of distill these models. I think it's done a lot in language models even. So they'll train like a 30 billion model and then train the 1 billion model to predict what the 30 billion model was outputting. So I can understand that it would make a lot of sense for like diffusion models as well. One thing that I did is, instead of like retraining the model to like kind of mimic or mirror what the 2 time step model was doing, I just basically fine-tuned it. So I trained it at for t equals 200 for like 1,000,000 steps or so, and then I just live changed the hyperparameter of t to like 20, and it worked really well. Training equals 20 from the start wouldn't be so good. It wouldn't learn as well. But live updating it like right at the end, so like sort of fine-tuning it on t equals 20, like that helped quite a lot. I wonder how that compares to like training different models that would like sort of replicate the performance. I'm not exactly sure. This is like the extent I've tried. And it worked well for me, so I didn't really think too much more about it. But yeah, that's a very, very interesting approach. I feel like it would take a lot longer though.
You have to parameterize things a bit differently when you start trying to do that as well. It's certainly a lot more complicated.
Yeah, for sure.
Yeah, Tim, if you can drop some of those citations and some of the references in the chat. Awesome,
thanks.
Yeah,
cool. So my question was, I've seen a few papers. So Tim and I and Carl, who's also in here, are doing models, generating terrain from like digital elevation models. Anyway, so we're doing like an image to image task, similar to like say a CGAN, which is not very common in the diffusion models I've seen. Like I know about palette and control net, but it's more about like giving further conditioning prompt rather than like pure image to image translation. Do you know why it's not so common to do?
So in this case, you're saying that your conditioning vector is including some image information in it as well.
Yeah, so actually the way we're doing it is we concatenate the like a conditional image to the the input to the model at each time step, and like without like noising it. And then we have an additional vector, but it's more about controlling the style of the outputs rather than and that's what we use as the encoding as opposed to clip embedding. But yeah.
Yeah, I guess it like depends on the use case, right? Like, is there many use cases for this sort of thing? I can see how it would be used for like terrain generation. Here's a picture of my terrain. Now, like, give me the actual heights of each of the things, each of the locations. Yeah, I think I've seen like a lot of random literature of people doing random conditionings or like different conditioning. Some people condition on speech. Some people, like us, we condition on speech. So you can do it, I'm pretty sure, and you can definitely condition on the image. So like you're diffusing your terrain vector, right, or whatever representation you have, and then in your conditioning you have some text prompt and then also your image, which might like look like your text. Is that what you're doing?
Yeah, so we actually got rid of text completely, and it's literally it's basically like a sketch to terrain thing. So we give a sketch of like a low detailed sketch, and then it learns to generate the detail that makes up a realistic terrain. And then there's like the embedding is a vector derived from a real terrain to guide the style. So you can have like mountains or cliffs or plains or whatever. So that because the sketch doesn't really encode that information directly.
So is that like additional conditioning you're also adding? Okay, that makes sense.
Yeah,
that's a very, very interesting approach. It should work. I don't see why it wouldn't. Like you can kind of put whatever you want into the conditioning as long as it makes sense in terms of the model. So just make sure that the model is attending to that correctly, and you have like, I would possibly even use like some pre-trained encoder for the input image. I don't know what necessarily, maybe even clip itself or ResNet of some sort, just to get like a really rich representation. So something we also tried is you can actually train the encoding portion. So I mentioned earlier you can use a frozen clip model, but you can also train that model if you really want to. It will slow down your training quite a lot though. So I don't know how much training you're doing, but something I should have mentioned during the training section is these models take really, really long to train. Yeah, in my experience.
Yeah, we have like 100.
Yeah.
not quite the same as stable diffusion, but
yeah, I think like for my recent model where we did this, I think I trained on an A100 for a month or so. Yeah, so it does take quite a long time. I see.
Cool, thank you.
Linked papers here.
Yeah, a couple of papers there that look at neural ODEs and just plain old ODEs for
that's very cool.
This up. I had another quick question about so I think we've had this massive acceleration in how good these types of generative models are, both in terms of diffusion models and in terms of LLMs, and I'm really interested in the intersection of them. So I know when I was playing around a little bit before, just using diffusion models, they were very impressive at some things, and some things they were very bad at, in particular negation. So draw me a picture of an animal which is not a dog. It was really bad at parsing what that meant, presumably because most of the training it's done on doesn't have any concept of negation. That's not very common. It's really far out of distribution. But clearly combining that with an LLM, the LLM is then able to come up with an idea of the thing, and
yes,
and it can then do it. Have you seen any interesting interplay between LLMs and diffusion models? particularly interesting uses of them?
Not currently. One thing I maybe want to comment on is the negation thing. So in almost all modern models, they have a negative prompt as well. I don't know if you've seen that.
Okay.
So you have your like normal prompt, and then you also have a negative prompt. So these are the things that you don't want to include. I'm not exactly sure how they like condition it like that, but it works really well. So if you say like, I want a robot, but I don't know, I don't want it to be humanoid. You put humanoid in the negative prompt, and it won't ever generate a humanoid robot.
Okay.
It's really good at that. So a lot of the new models include negative prompts. I think even if you go onto the Hugging Face Stable Diffusion, it's the latest version does also have that as well. So if you want to look into that. In terms of LLMs, I think I have seen some people like, they'll like, you put in a prompt and then they've sort of, I don't think they even fine-tuned it. They're like, okay, give me a stable diffusion prompt out of this. And I haven't seen any papers or official literature doing that, but people just playing around. So like you'll ask it a question and then it'll be like, okay, produce the tags for an image that would represent this text. It seems to work pretty okay. I think in terms of like the negative image stuff, your best bet is probably your negative prompt though.
I mean, it's interesting that problem is solved, but it sounds like it's almost solved in quite a handcrafted way. Like you'd like it to be emergent.
No, I do agree. It is a very interesting problem. Like, how do you, because like all of these images, they are positively labeled. You don't really get negative labels or negatively labeled data sets. So I think that's literally what they do is they take the pre-trained model and they're like, okay, go away from this in the embedding space. Kind of like that classify free guidance. They're like, move away from the third one, which is conditioned on the humanoid. I think that's how they do it, if I had to guess. That's a very interesting, like reinforcement learning and LLMs and diffusion all combined into some kind of emergent behavior would be really cool.
Sinjin.
I was wondering in terms of the sort of negation aspect or logic in general. I know a lot of these models like to be prompted quite specifically. So, but the problem would be when you try to like negate or logic, or let's say you go from wanting a very specific dog to having not a dog, you know, your space grows dramatically to like anything possible. I wonder if that would result in like much worse sort of outputs, even if it finds like a sort of guide just because of the space is so large. Have you seen anything on that?
I haven't encountered that in like my own like playing around with these models. I don't know how they actually manage that. Like, why doesn't it? Because obviously like it's easier then to like go in any direction away from your like negative prompt. Why is it still managing to latch on so well to your positive prompt? I guess maybe they just have like a really fine-tuned way, like smart way of doing it, or smart way of interpolating between the two. I'll have to actually look at the code and how they actually do these things in like the papers. It's really interesting.
On that as well. I'm sort of thinking about, has anyone looked at this from a hierarchical perspective where you sort of have like a meta diffusion? Because I guess one of the things with sort of question about continuous time and discrete time steps and learning step by step is that you essentially have this sort of inductive meta heuristic where you're saying that the best way to learn is to sort of take one small step at a time, like a curriculum. But it'd be interesting to see if that's learnable. Like, is a certain different type of curriculum result in better performance for certain types of prompts? So like maybe you could have something that would control that process in some way, maybe like evolution or RL or something.
That would be really interesting. Some very cool things that we could probably do with these models.
I'm just wondering. Sorry, go. I was wondering whether one can think of the probabilistic, the distribution shift that you're looking at somehow as the learning in a generative model. And maybe I'm painting everything with the same brush these days, but I wonder if there's an active inference picture of diffusion models.
Interesting.
I guess.
Something I like to say, but I don't know how valid this is. I actually say that diffusion models are kind of like GANs, where the discriminator is just a fixed KL divergence loss. So they are kind of like GANs or generative models in that sense. If you really want to
but so a generative model in the active inference sense, which is a bit different.
Okay.
It's sort of related to a world model where
yes.
has access to observations and builds up its model based on those observations. But I mean, there you're also looking at a KL divergence between predictions and observations. Yeah, that may be taking it a step too far, but I'll do a little look for that.
Yeah.
Awesome.
Very interesting.
Any other questions? Cool. If not, thank you again, Kevin, very much for a really lovely talk. Yeah, and hope to catch you around sometime very, very soon. And you're welcome anytime to come along to the Shocklab talks, either to give another at any point or to just join and watch. Awesome. Thank you so much. Thanks everyone for coming.
Thanks, Kevin. Cheers.
Thanks.
Cheers. Thanks, Ajay.
Bye-bye.